Now continue with the technical session. I'd like to ask Hervé Michaillet of Legy to come forward. Hervé did his research in the shell flume at Deltares. His presentation will be about Globex. He can explain himself what Globex stands for, and it's about wave dynamics on a shallow sloping beach.
Thank you, Peter. Good morning, everyone. So I'm going to present you a quick overview and a few results of this Globex project. I aim to study wave dynamics on a shallow sloping beach. So many participants to the experiments, most of them are co-authors of this talk, and also involved in the processing. So Globex means gently sloping beach experiment. And so the aim was to collect high-resolution data sets of wave transformation on a 1 to 80 fixed beach for a range of wave conditions. Say most of our knowledge comes from theoretical studies, field experiments, and for the lab experiments they were mainly for steep slopes. For instance, reference paper by Van Dongeren et al. In 2007 considered one of the 35 beach slope. So we studied wave nonlinearity, quantified in terms of skewness and asymmetry, related to infragravity waves, their generation, dissipation, and possible reflection from the beach, estimating the wave celerity of individual wave crests, and also use the opportunity to study the transfers inside the bottom boundary layer. The project was divided in 5 work packages listed here, and I will just insist that there were about 24 participants to the experiments from 11 research institutes, and with a great help from a Deltaized support staff. So the experimental setup, as I said, 1 to 80 concrete beach slope. It was done in the shelled flume at Deltaized in Delft in the Netherlands. The waves were generated with a piston type wavemaker with active reflection compensation, so to absorb any potential long wave coming from the beach. The horizontal section before the slope were 16.6 meters, and the water depth was there 85 centimeters. Experimental program consisted in 8 different wave conditions that were repeated many times so to measure all along the beach. The 3 first one were irregular waves complying to a chance swap spectrum, where we played on the significant wave heights that were different from different conditions, and also the peak period, and also the enhancement factor in one case, so to make a narrow banded spectrum. More synthetic conditions were bichromatic waves, defined by 2 frequencies, F1 and F2, and related amplitude, A1 and A2. For those ones, the difference F2 minus F1 define the period of the group, 15 seconds in one case and about 24 seconds in the 2 others. The last one were more modulated, as we can see from the amplitude of the second components. There were also monochromatic waves. One is a long period wave, 24 seconds, and the last one was more short waves and more related to the determination of the roughness for the study of the boundary layer. Here in my presentation I will focus on the B3 condition, that is the more modulated and that show a great wealth of processes. In the graph on the bottom there are many blue dots that were the locations of the different wave gauges moved all along the flume. So to point out there were 190 measuring positions. The circles are the location of velocity measurements. The red circles were made with acoustic Doppler velocimeters, boundary layer measurements I will briefly show afterwards. So the instruments for, say, the waves and swash were 21 wave gauges. They were installed in trolley, as you can see on the picture on the bottom left. They can be moved all along the flume. There was also a swash wire, so to try to get the run-up and backwash. An acoustic Doppler velocimeter on the right. Also on the bottom right, a video camera. We recorded experiments with two cameras installed on the top of the building and also from the side. And there was also a terrestrial laser scanner, so to accurately measure the bed elevation, also to try to capture the bores coming up on the beach, as you can see here in this picture. So from the video from the top is an example of what we can get. It's called time stacks. That is from, say, okay, the horizontal axis is the cross-shore direction. And by taking a line of pixels in an image and taking the next one from the next image, you stack them until you get a full spatial temporal diagram. Okay, the time is the vertical axis. So in this picture, you can see nicely how short waves can be catch up by bores propagating. This is a bichromatic condition, so we repeat all the time the same group. So we can have one group riding on the shoreline here and another one there, or some details that is, for instance, secondary waves or ripples generated at the back of the leading wave. Same sort of representation on the top left here. This is from now the wave gauge measurements, but it's also the cross-shore location and the time going up. And where you can see that the red lines are each shortwave crest. If you low pass filter the signal, you have the picture on the right. So that's only low frequencies, and this is showing a nice standing wave pattern. So one of the difficulties here is to separate what is incoming to the beach and what is reflected from the beach. So you can estimate that by analyzing co-located signals, free surface elevation eta and the horizontal cross-shore velocity u, and so you get this pattern on the bottom left, incident waves, and reflected waves on the bottom right. This is difficult to discriminate in the braking zone, around 60 or 65 meters. And say the project was also the opportunity to develop new tools. For instance, here we have the results from an analysis by the radon transform that had to complete the picture, have a lot better accuracy on the estimation of what is incoming and reflected from the beach. Here are examples of free surface elevation. This is a wave group where you have on the very top here where we clearly see the modulation. So this is recorded in the horizontal cross-section before reaching the slope. Just below that's in the braking zone where you can see that, yeah, waves are a lot more peaky. And then evolving in the surf zone below and in the swash zone on the right. One of the points here is that we clearly show that the short waves that are riding on the long wave crest made by this modulation propagated a lot faster, and so to merge at the bore front. To just point that the bore is propagating a lot faster than the linear phase velocity that is represented by the dashed red line here. To go a little bit further, we compare the measurements with Boussinesq type model, SerriD model. Time series measurements of free surface elevations in the gray thick line, in the breaking zone on top, in the surf and the swash at the bottom. There are three colored lines corresponding to model results for different breaking parameters that are the breaking index, the front slope of the wave, the dissipation coefficient of the roller, and to show that depending on these parameters, changing them slightly, we may more or less reproduce the merging of the short waves. But yeah, all in all, the agreement is quite pretty good. In terms of statistics, on the left column, that's free surface elevation. On the right, that's crash or horizontal velocity. The measurements are the gray circles, and again, the model results are the different colored line. So, for instance, on the top left, that's the wave set down and set up. Here it's the standard deviation of free surface elevation that is related to the wave 8. So that match very well, for instance, the breaking point and dissipation in the subzone. The thick lines are the low frequency waves, so again a very good agreement. And on the bottom, that's the wave skewness, that measure the peakiness of the waves. And on the very bottom, that's the asymmetry that quantifies how much the wave has a sawtooth shape. It's how the front of the wave is steep. We may note that the comparison of the measurements with the models is a bit difficult for the velocities because the model integrates the values of the wall water column while the measurements are made at the signal point. But we may note that we have very large fluctuations of what we can estimate of this mean velocity, or also called sometimes the undertow, very large fluctuations in the measurements that can be related to some peaks in the skewness and asymmetry. But I have to say that these are things we don't know, don't understand so well so far. But well, again, all in all, comparisons are not that bad. Very briefly, I will talk about the boundary layer measurements. They were made at two different cross-shore locations on the beach with two different systems. I will focus on the laser Doppler anemometry that has a resolution of 100 microns. And for instance, here on the time series on top, these are ensemble average horizontal velocities. Again, because we repeat all the time the same wave series, we can compute the ensemble average velocity. And for instance, you can note that outside of the boundary layer, that's the black line, that is 1 centimeter above the bed, some waves can be very asymmetric with a very steep front face and a gentle rear face. That's going down into the boundary layer, that's the green signal, that is 250 microns above the bed, that's the green line. The signal is a lot more peaky and a lot less asymmetric. On the bottom left, that's total spectrum. Here you can recognize that we have many peaks corresponding to the different harmonics of the signal. And if we remove the ensemble average signal from it, we can get the fluctuations on the right, where in fact we have a nice decay with the frequency as a slope of -5/3 that's characteristic of turbulent decay on about two decades. So from that we can have vertical profiles. Again, resolution is about 100 microns. On the left, that's a standard deviation where we can recognize low glow trend. On the bottom, here, or very close to the bottom, we may be influenced by local roughness due to the sand grains that constitute the concrete bed. On the right, that are the fluctuations. You may note that it's almost uniform for the vertical fluctuations, while the horizontal fluctuations tend to decay towards the bed. We have also the mean velocities on the left, where we can point out this boundary layer streaming in the very first millimeter above the bed. Finally, on the right, the skewness and the asymmetry I talked before. You may note that for the asymmetric waves, the asymmetry tends to decay towards zero at the bed, while the skewness is in fact increasing towards the bed. So here I draw my conclusions. I hope that you are convinced that we collected a high resolution data set with a large number of instruments. With the analysis of cross-shore variations and also vertical variations for a few locations, few cross-shore locations on the beach, to study the wave nonlinearities related to inferiority waves interactions. And so, among others things, to improve breaking parameterizations, estimate wave celerity, and also studying nonlinear transfers through spectral and bispectral analysis. But this is also ongoing work, of course. So thank you for your attention.
Thank you, Hervé. We have time for questions. Are there any questions from the audience? Can I start with a question then? Sorry.
I was going to ask by how much you had to vary the breaking parameters.
Sorry?
Please use the microphone.
I'm sorry. By how much did you have to vary the breaking parameters?
To get the few numerical results I showed is changing very slightly the breaking parameters, in fact. For instance, the breaking index is 0.8, and changing slightly to 0.75 can change dramatically the things. In fact, we can say that considering the dissipation of these short waves, to get the correct merging, it's very sensitive to this quantity, for instance.
Any more questions? Then I'm going to take this opportunity to ask mine. I was wondering how the photo time stack, which is an instrument, compares to the wave gauge data.
It's a bit difficult because what we have from the video is the brightness that is linked to the slope of the front wave and also of the size of the roller. The roller itself produces some brightness which is whiter, okay, and so the correct relation between, let's say, for instance, the wave height measured by a wave gauge and the brightness recorded by the video is not that easy. Okay. On the other hand, for comparing for wave celerity estimates, for instance, it might work quite very well.
Okay. Question there?
Quick question is, was the laser scanner only used for bottom profiling or was also used for the video measurement for the lightning of that?
The terrestrial laser scanner was the first step to measure accurately the bed profile. So to check that, in fact, it's very, very close to 1/80. The other idea was trying to get to estimate the balls propagating on a beach, also try to get the backwash. I have to say that on this very shallow beach, one of the difficulties was also to clearly see where is the maximum rundown. Also with the terrestrial laser scanner, it was difficult to get it. But that's also related to the previous presentation of Peter. It's a difficult task, in fact, to measure correctly the backwash when you have a very thin layer of water running down the beach, especially for this very shallow sloping beach, because you still have a very thin layer of water running down. It's difficult to take the maximum rundown of it. I always also try to use this instrument to get it.
Okay, let's thank Hervé again for his presentation. And I'd like to ask Michael Paul to come forward to give the next presentation about one of our JRAs in Hydrolab. This one concerns Pisces, and the title of the